Well, hello. Welcome back to another episode of Undercooled, a materials education podcast. Today, Tim and I are going to talk about demonstrations, mostly because this was Tim's life for quite some time before he became a lecturer.
Sure
And so
was.
let's start with having Tim tell you what he used to do. Go ahead, Tim.
Sure. Uh, Once upon a time when I started in MSE, my first job in MSE was being the support guy. So part of that was helping out with lab classes, but another big part of it was developing and implementing the classroom demos mostly for our intro classes, a couple advanced classes as well. So it was a great learning experience for me. Hey, what is all this stuff? It was a good way to get into the field, but working with different faculty to come up with ideas for demos that they wanted to do in their classes, then trying to help make those real was a really interesting bit of work that I did, and something I would definitely recommend to anyone who wants to figure out a little bit more on the teaching side.
Great. So why demos? What do you think the value of a demonstration is?
You know, I could see three main arguments in favor of having classroom demos. One of them is engagement. They're fun. That's in its own right. There is some value to that. That's not going to be enough by itself, but sometimes you just want to say, hey, let's do something different and interesting to bring the students back to life a little bit. So that's fine. And for that, almost anything works. The second aspect, and the one that I'd argue is the most important out of these three, is the fact that you can have students make and test predictions in real time, live, while they're learning the content, and to have a much faster feedback response than what you get in a real lab when you're doing experiments or when you're doing simulations. You know, that can be a year's effort to find out whether your prediction was correct. So to find out in minutes, do I understand this? Am I thinking about it correctly? That's very powerful. And then the third aspect is that demos can be used as a launching point for a further investigation on the student side. So that can be a way to develop into an out-of-class assignment like a homework, for example. And that can be a nice way to say, okay, we're learning this stuff in class, but now go out and connect it to the rest of the world.
That's pretty good. So, of course, I've been teaching intro to materials for a very long time, and I don't think I could do it without doing demonstrations. Otherwise, it's just us talking, yap, yap, yap in front of the class, and they don't really believe that anything I'm saying is true. So at least the demos show that there's some real life thing going on. And I tend to far prefer physical demonstrations to all the virtual demonstrations that have been coming up. I've seen a lot of them, and in my opinion, I just don't get it. They seem like very black box modules where you have little sliders to change parameters, and you just look how the math changes. And that just kind of leaves me kind of flat. And there's no connection to the real physical world when you do that. Whereas when you try a real physical demo, you heat something up, you stretch something, you bang on it, you do something to it, you actually see it respond. And it's hard to deny that that's a real thing that just happened. And so to me, physical demonstrations are so powerful. Besides all the three things you just mentioned, I think they're just powerful because they expand a student's everyday experience. And I don't think everyday experience should ever be discounted. It's what we are. We grow up, we fall down and it hurts. We run into a wall
Yeah.
and it hurts. And it's a real thing to anybody who's experienced any of those things. And unfortunately, everyday experience doesn't always serve us well. And that's kind of our job as educators, to explain to students that, yeah, you know a lot, and we really value what you know, but there's a lot you probably don't know. A lot of things you haven't quite experienced that we want to make you aware of, because if you can understand these concepts and these ideas that we're trying to teach you, and start to believe it and start to fold it into your everyday experience, you're going to develop a really high quality intuition that will help you design things using the fundamentals of material science. It's kind of what we do. And so doing demonstrations, I think, is just a critical part of teaching material science. So at least that's how I feel. I never cared much for these the physics PhET demonstrations or JavaScript things because, yeah, they're kind of cool, but they illustrate certain things, but they don't really add to that individual experience. And I think that's really special.
Yeah, I definitely have to agree on how important students' individual experiences are, both what they bring to the class as well as what they experience in class. And this is where the right demo at the right time can be so powerful, because if students from their everyday life and from their prior experience, if they have one expectation about how a material should behave, and then they see it in real time, live in front of their eyes, behaving in a different way that's not what they expected, that can be a really powerful catalyst to get them to evaluate how they understand the content that we're trying to teach.
Right. Now, of course, the kind of demo that you would choose depends pretty much entirely on who the audience is. So, we've kind of just been talking about intro to materials courses, because that's what you and I do the most of the time. But there's a lot of other audiences, and I think you have to tune the demo to the audience to make sure they'll be able to receive it and get something out of it. For instance, when you go into a K through 6 class doing outreach, you're probably not going to show them the zinc aluminum system where you get this metastable state and you smack it and it gets hot. They would have no chance of really understanding that. On the other hand, liquid nitrogen ice cream, wow, that's a fun thing for little kids to do, and it connects with their everyday experience with eating ice cream. And now you can talk to them about how you can change the texture of that ice cream by changing the kinetics of that experiment, which is kind of cool.
I love that example because that is one that really does work at all levels, exactly as you described. Even for a young child, it's ice cream, but then that can go all the way up to an undergraduate or even a graduate kinetics course where you're looking at the nucleation and growth of ice crystals and how this is affected by the cooling rate and by the ratio of nitrogen to cream and these other factors. It can become very complex or not, as you want it to be. And that's something that I think we should try to aim for with all of our demos, is that they really do work at multiple levels, so that we're not trying to create entirely new suites of content for every separate audience.
And that's great if we can pull it off, but sometimes it's hard. So like silly putty. Yeah, we do use that to show viscoelastic behavior at any level, but it's a really simple concept, at least the silly putty part. So that's more amenable to K through 6 or high school students, even intro to material students. But I don't think we want to be pulling out silly putty for a graduate course in polymers. I think they know that. But the other kinds of demos that we do all the time, a lot of us go into high schools to try to get students excited about material science so that they might choose a materials career. And so I know you've done a lot of this, I've done some, and I think the most exciting tool that we can bring to high schools is the portable scanning electron microscopes. Maybe you can talk a little bit about how we do that.
Sure. The future is an amazing place. You can just take an SEM and carry it around in the back of your car now. And there are tabletop models made by a variety of manufacturers now that we've taken to classrooms, to museums, to public science centers even. And, the power of that, this will also connect back to your point about virtual demos, I think. One of the things that really makes materials science special is how we work across so many length scales. And to be able to zoom in real time from 10x to 100 to 1,000 to 10,000 to 50,000, and to see a single object at so many different length scales can really be a mind-blowing experience and get people to think, I didn't even know that existed. So I am very glad that we have the ability technologically to do that now and to bring that to people instead of having to wait until they're already in the university.
Especially when you show them things like shark skin, because they hear about the Olympics and, athletes wearing these shark skin bathing suits for swimming, which are outlawed now because they work too well. And, but to show them what shark skin actually looks like, to show them how butterfly wings are really diffraction gratings, and that's why you get all those weird colors off the wings when they shimmer. Even just showing them, the width of Lincoln's leg on a Lincoln penny, because his leg is 100 microns wide, and you can just barely see that on the penny with your naked eye, but you can really see it in the SEM, and it just gives a way to connect with real life at all these different length scales. And, I think that's really important for high school kids because they haven't really appreciated that yet. Whereas college kids and certainly graduate students, they understand all that. So, but you can use the same tool to do other things for the graduate students, looking at twinning and all this other neat stuff. And then the other place we use demonstrations is when we go to career fairs or majors fairs, where we bring things to try to get people to come to our table, to come to talk to us, so we have a shot at convincing them how cool material science is. And those are a little different. I mean, I think the demo I've always liked the most is the one with the CD that you squish in there, you spray that stuff and it slams out. Things that blow up or explode really get the students excited. Maybe you can
as soon
talk
as there's
about
a
that
crowd of people with everyone wearing safety glasses and loud noises happening, and the whole room wants to know, whoa, what's happening over there? That must be the cool kids table. So it can certainly be a good way to rope people in. That particular demo, how it works is you have to acquire these legendary artifacts known as compact discs. They come from a previous age. And if you can get enough of them in one place, what you do is you put the CD under some flexural stress. So have a mount that you can clamp it into and squeeze it a little bit, and spray it with furniture polish. And what will happen is that the furniture polish will change the cross-linking between the polycarbonate chains in the CD, and it will reach the point where the strength of the polycarbonate changes, but it's still held under this constant stress, and eventually it fails. And so the CD will snap and jump out of the holder into usually a few pieces, and it's a really great way to illustrate that chemical stresses and chemical processing of materials alongside mechanical stresses are really important to understanding processing and materials properties.
Yep, that's a cool one. And then finally, another really important kind of demonstration for the materials community is what we do with our teachers' camps. And you've been involved with the teachers' camps for years, Tim, and maybe you can talk about, they have a different set of boundary conditions, right? Things have to be cheap, and they have to fit into lesson plans. And that's been pretty much the hallmark of the whole ASM Foundation teachers camps, is showing these teachers how to do these demonstrations in class as part of the curriculum. And so maybe you can describe some of those for us.
Yeah. The ASM teachers camp, anyone out there who's listening to this, if there is one in your area and you haven't interacted with it, I would absolutely recommend that. It's a great experience. It is a good way to build relationships within your community as well, and also a good way to pick up some good tips for your own MSc classes. Here's a couple examples. Many of them are quite chemistry oriented. A lot of the schools where these teachers are teaching don't have a materials science class. They might have a quote unquote engineering course. Some have physics classes, but mostly they're teaching chemistry. And so they're approaching really materials science from the view of what can a high school chemistry student engage with. So they're looking at crystal growth and single replacement reactions. For example, there is a demo that they do where students take a galvanized nail, they immerse it in a copper, I believe it's a copper chloride solution, and they grow metallic copper off of this nail as the copper replaces the zinc atoms on the surface of the nail. So that's a really great one. And another example that we use all the time at the college level is the iron wire. It's truly one of the classic greats of MSc demos, I feel. And Steve, I know you use the iron wire in your classes as well. So can you talk us through that one?
Yeah, I love that one. This is, of course, where you take piano wire, which is a very, very low carbon steel, almost 0% carbon, and you stretch it out and you do something you tell the kids, don't do this at home. And you take the two ends and you plug it into a variac and you just crank it up. And as the wire gets hotter and higher, of course, you get thermal expansion. But it's two effects that you're trying to teach. One is thermal expansion. And of course, the other is the BCC to FCC phase transformation of iron. And so as it's heating, it starts to get hot, red hot, and it's sagging. But right when it hits the transition to FCC iron, because FCC is more close packed than BCC, it's a volumetric phase transformation. So it shrinks. So it goes down, then it goes up, and then because you're still heating it, it eventually expands and goes down. And it's really obvious when you cool it. So once it's glowing hot all the way down above, it's an austenitic material, you just turn off the variac and it comes back up and then it drops down and then it goes back up again. And most students get the thermal expansion part, but very, very few remember about the volumetric phase transformation because that's kind of a new concept for most students. Most students, they come into college and they've heard of phase transformations. They know you can go from liquid to solid to gas, and that's it, right? That's all you learn in high school. And now we tell them that a phase can be different crystal structures. And that is kind of very disturbing to them because it's challenging what they thought they understood. And now we tell them that there's more to it. And so what is a different crystal structure? Well, there are, you can show them X-ray diffraction patterns, but I don't know if they're going to believe that. But if you show them a volumetric change and how it's reversible, it goes up and down. And then I tell them how when I was a graduate student, I used single crystal iron samples they were very expensive because you can only make them with something called strain annealing. So my little tiny sample was like $800. And once I made the mistake when I was sputter cleaning it, I had 2 wires spot welded to it, right? So I would heat the wires and it would get hot. Well, I took it up too high. I took it up above the BCC to FCC phase transformation. And yeah, it came back as BCC, but it wasn't single crystal anymore. Right. It was a mess. And my advisor was very kind to me and said, don't worry about it. Just don't do it again. And he bought me a new one.
That's very nice.
But it's, you get, those of us who do these things in research, we get burned all the time by our demos, which brings up a really interesting point about demos. You kind of have to have a sense of humor because they don't always work. In fact, it's very easy to have them not work.
Yes, they will betray you when you need them the most.
Right. And a lot of that has to do with the person who sources the materials, puts it together, trains the graduate student that's going to run the demonstration, And often the only way for that person, namely you, to really know that you have a handle on this was for you to actually come to class and do the demo yourself. So you felt extremely comfortable that it would work. Then you would be in a position to show somebody how to do it. For example, the iron thing, it doesn't always work, right? And it doesn't always work because if you use one piece of wire too many times, you get all these grain boundaries and nanocrystalline material, and it just messes everything up because those grain boundaries pin the transformations. And so the trick for that is to always start with a fresh wire. And so, where do you learn that? Well, by experience.
By doing it a few dozen times and seeing when it works and when it doesn't, and finding out what the stopping points are. Another one, I use this to get graduate students all the time because another factor is how quickly you turn up the temperature on the wire, because you're feeding it current. That's your heating mechanism, is joule heating, and the resistance is a function of the temperature. But often a novice implementer of this demo won't be considering the fact that the resistance of the wire is changing. And so they crank up the current, and then it blows the fuse in the variac, and then nothing happens at all. And I did everything right. What went wrong? Well, you forgot that the resistance is lower when it's colder and you fed it too much current and the fuse couldn't handle it. But if you ramp it up slowly and let that resistance go up as well, then... So there are so many little subtleties like that, yeah, you should, if you're bringing a new demo into your class, I would, no kidding, recommend practicing it at least a dozen times before doing it in front of the students if you want to have a good chance of success. If you want a model is how to handle things going wrong, oh yeah, jump right in and give it a go. Something will go wrong for sure, but usually we want more than that.
Another favorite demo when you want to show strengthening of metals, you take a pretty much pure aluminum bar and you anneal it. And then when you anneal it, pure aluminum is very soft. You can bend that bar very easily. And then hopefully when you bend it, you've introduced enough dislocations that it's very difficult to bend it back. And so it sounds great in principle, but I can't tell you how many times that demo hasn't worked. Either the bar wasn't annealed enough and I could barely bend it to begin with. You like to do this by asking someone who thinks they're really weak, but would like to demonstrate they can bend metal. And you have them come up. And if they can't bend it, oh my God, it just ruins the whole thing.
Yeah.
But the other problem is if it's too annealed, yeah, it's easy to bend, but then the strong people in the class can actually bend it back. And that again, takes your thunder away because you want it. I mean, I'll never forget, I had one bar that was perfect. This very weak individual was able to just bend it. It made them feel great. And then I said, anyone think they're a really big, strong guy, guy or girl? And this Marine came up.
Oh boy.
His fatigues. And he couldn't bend it back. And I thought he was going to kill me. I thought he was going to, because he was so embarrassed that he couldn't bend it back and he was a Marine. And so I was like a little fearful. But that was exactly what you want to happen. So how do you hit that just right? And the only way to really do that is to have enough bars so you can try one. And so if I've learned anything about demos, it's all the things that can go wrong with a demo. And it's going to happen, and you're just going to have to explain to the students that this is real life. It's complicated, and lots of different things happen. But luckily, something you said earlier is so true. What really is important is that students make a prediction before you do the demo. And I believe Eric Mazur has written some education research papers demonstrating this and showing that if the students can predict what's going to happen before it happens, it doesn't matter if they get it right or wrong because they're roped in. Once they've made a prediction, they've got skin in the game. They want to know what's going to happen. They want to see if they're right or wrong. And so they end up paying much more attention, and then they want to understand why. And so as long as you can produce a good reason why, even if the demo doesn't work, if you can tell them why it didn't work, they'll actually learn a lot. And ultimately, our job isn't to make the demos go great. Sometimes it's good they see that we fail all the time because that's normal, not the other way around.
Yes,
but what
very
really
much
matters
so.
is that they learn the concept and bring something into their everyday experience that they didn't have before to give them the ability to think about how more complex things might happen in the future.
Couldn't agree more. What are some other greatest hits that we have? We've talked about a few metals ones.
There's a lot of polymer ones.
Yeah. I
mean,
know one polymer demo that I really like because it also brings in functional properties a little bit is making polarizers. That's something
Right.
that's very low cost, very easy to do, and looks really cool, but also reminds students, hey, there's more to life than strength and Young's modulus and things like that.
Right. So which one do you like?
So I've tried it a couple different ways. I've found the best results with garbage bags, actually.
Polyethylene.
I'm not sure if it's
garbage bags.
yes, polyethylene garbage bags, to be clear. Well, also to be clear, but the trick with those is getting the strain rate right so that you can strain them far enough to get some good alignment of the polymer chains to build in that anisotropy so they become polarizing without actually tearing them. And that can require a little bit of a delicate touch, but it's one of those things you practice it, and as soon as you get it right the first time, you say, that's what I have to do, and it's pretty repeatable after that. But it's also something you can have a whole class do. Buy a box of garbage bags. No big deal.
Right. But you know what I find the most challenging part of that is to demo that in front of the whole class? They got rid of all the overhead projectors. Right? That was the perfect place to demo it. So if two people held polarizers, right, showed that when you cross them it goes black, then open it up, then with those two people holding those, another person would come in and stretch the polyethylene garbage bag and then rotate it. And while it's not as even as a polarizer, you can definitely see all the changes in the intensity on the screen. But they got rid of that. And document cameras don't quite cut it because not enough light goes through. And so it's a little harder to do. So I wish they'd bring back some overhead projectors just for that demo. Those things were great. The other one I really like is how you can have students feel entropy. And that, of course, is the rubber band one. Have you seen that one, Tim?
Oh, yeah. And
so it turns out that your forehead is very, very sensitive to temperature. So if you take a rubber band, you just pull it, stretch it, and then you, if you pull it really quickly and put it to your head, it feels hotter. And why is that? Because all those elastomers are sliding along each other, creating friction, and it's getting heated, just joule heating, right? But then if you take your stretched out polymer and you release it very quickly and put it on your head, it is noticeably cold.
Cooler, yep.
It's colder than your ambient was. And why is that? That's because all those ordered chains have disordered, and entropy and temperature are intrinsically related. And so you can feel entropy. And what I like about this one is every single student gets to do the demo themselves, which is ideal. Unfortunately, with large classes, we can't always do that. But with rubber bands, they're so cheap, you can pass them all around. Now you see everybody pulling these things, and it's just
Sticking
great
it
to
on their
watch them
foreheads,
experience that. And, entropy is a hard concept to understand. And hopefully this will give them some insight into it. And the very fact that polymers are these big chains that are either ordered or disordered, it should work. And that's one that almost always works.
Mm-hmm.
The other demo I really like is when you teach fatigue. So fatigue is very statistical in nature. It's not very, what's the word? It doesn't, there's a word for this. It doesn't follow from first principles, right? It's not reproducible in the way that, the number of dislocations when you strain something might be. And it's, there is a lot of noise. And it's because the origin of fatigue is a flaw. And you don't know what the flaws are or how they're distributed in the material. So when you stress, even though you're doing it well below the yield stress, you're still accumulating defects and accumulating and changing internal flaws, cracks, all of this stuff. So finally, when you do it too much, it catastrophically fails. And that's why fatigue is so dangerous. So little things like when, you teach mechanical properties, you want students to understand how to calculate an appropriate safety factor. And it's usually pretty easy. You choose at least 2, maybe 10, and you just multiply, the expected maximum yield stress that you're going to have on it, and you're done. You can't do that with fatigue, because for fatigue, you need to understand the probabilistic nature of how it fails. So those SN curves, those are just the 50% line curves. What really matters is how all the data is collected and how it distributes. So the 90th percentile, how far away from that 50% line is that? And that's going to be different for different materials, different processing conditions. It's complicated. So to try to illustrate that to students, we give them paper clips and make a quarter of the class bend it 90 degrees and back. That's one cycle. And they keep doing that. And each person reports their own number of cycles to failure. Then the next quarter of the class does 180 and back, 180 and back. The next one does 270, and the last group does 360. Well, the 360 group, of course, those are going to fail much earlier.
Right.
But you're also going to get a much bigger spread of the data. And when we look at the raw data, we can show the students using the class collectively how much spread in the data there is and how that spread changes for each of these different, well, we call them loadings. It's really not quite fatigue, but it's a strain version of it. And I think that's a really valuable thing, and it helps them understand that. The other demo we do, it's gotten a little, what's the word? It's what we used to do, we don't do anymore because some people get embarrassed. We used to ask everybody to report their weight in pounds. And even though it was anonymous, people got upset about it. So now we do height. We ask everybody to report their height in inches. And then we show the height average and the number average difference of those sets to talk about polymers with different lengths of chains, just to show them that you get different results depending on how you count and why it might be important. So those kinds of demonstrations, those are still participatory. They might not be physical, but you're still illustrating a point that's important. One demo I'd love to do, I don't know if we can pull this off, but it's the Da Vinci demo. Do you know which one that is?
No, what's that?
So Leonardo da Vinci, way back when he was alive, he did experiments and he proved that ropes that were longer were weaker than ropes that were shorter. And this usually blows our students' mind. The ropes are the same. But of course, it was because of Weibel statistics. And Weibel statistics is just weak link theory. So the longer a rope is, statistically, you're going to have more flaws in the longer rope, bigger flaws, leading to it failing because you'll have a better chance of a weak link in a long rope than a short rope. And Da Vinci did that. That's pretty cool that he did that. And so it'd be really fun if we had like some really long ropes and enough heavy weights to actually see them break. That would probably get expensive and take a lot of space up. But it's kind of a cool thing that he did that. Well before Weibel did his Weibel statistics.
Yeah, that would be an interesting one to try to turn into a full class activity. It'd be a matter of testing out different types of ropes, different amounts of weight, so on, to figure out what gives results that are sort of messy enough but still work.
And we kind of do that with one of our projects we do in our my intro class. Because I don't give exams, I have a lot of time. And because I don't lecture, I have a lot of time. So for the part of the class where we cover mechanical properties, my project is to build a mechanical testing instrument out of garbage. You can't spend more than $5. And so students are constantly, taking thread or taking Laffy Taffy and clamping things to them and looking how it stresses or strains or breaks. And it's a lot of fun. And that's another way to have students come up with their own demos is a really fun way. And then, of course, they have to explain to experts walking around the room why it happened. But it's just more engagement and it's more physical. And again, it just helps the student understand in a different context than just reading a book and doing homework problems how these phenomena actually work so that they can use the concepts that we're trying to teach them for whatever they do in the future. So what other demos? You've worked on a lot of demos. I don't know if you have the list I just gave you, but you can talk about some of those.
Yeah, I suppose we should round out with a couple of ceramics-oriented ones. So the first one that comes to my mind, I love this. This is also one that requires a little bit of finesse, but it is Glass the Conductor. I learned this one from the ASM teachers camps, actually. I've gotten several demos from them over the years. And the way you have this set up is that you've got a light bulb and you have an open switch essentially in the circuit feeding the light bulb, and you bridge that switch with a glass rod. And of course the light bulb doesn't light up because glass is an insulator, allegedly. But what people often forget is that processing is really important. And the demo, what you do is you heat the glass rod with a blowtorch. And as it gets hot enough, the mobility of the sodium ions in the glass, so you do want to use soda lime glass for this, it'll have a higher density of sodium ions in it. They get enough mobility to where they can actually carry enough current to light the light bulb. And if you really nail it just right, you can actually get it to self-sustain as well, where you take away the torch and the resistive heating from the current passing through the glass will keep the glass hot enough to keep the mobility high enough that current can keep flowing. And the ASM master teachers who have done this a zillion times, I've seen them keep one going for something like 20 minutes before it finally petered out. But yeah, conducting electricity through glass with the application of just a little heat, that's always a winner for me.
Well, and it's also really important to explain to students that it's not just electrons that transport charge.
Right.
Many things can transport charge. It's a charge carrier, not an electron. Some things are holes that are the dominant carrier. Some things are ions, like in the example you just showed. Sometimes they're solitons, double bond flipping,
Yep.
that make things move. So it's the fact that the ideas of conductivity and resistivity are very general, and they span across many different kinds of charge carriers. And that's a really important thing to get students to understand. So it's great for them understanding glasses, but it's also great for them understanding electrical properties.
Yep.
What about the making copper from malachite? That's another ceramics one.
Oh yeah, rocks are ceramics after all. There's this is one that is so fun to do with students partly, of course, it involves smoke and fire, and so that's exciting. But it's a really great illustration of this very, very old process of turning rocks into metal. This is, I don't know, 5,000 years old technology at this point, and still quite relevant today. So how it's set up is that you get a piece of charcoal, not like a briquette, but a good lump hardwood charcoal, large piece. This is your carbon source. And you can carve or drill a well. You're making a crucible, right, in the charcoal, and you load it up with some flakes of malachite. And you heat it. Again, I use a torch. And as you heat it, you're going through a series of chemical reactions where you are making carbon monoxide and carbon dioxide as you make the charcoal react with the air, and then you have the reactions between the malachite, which I'm trying to get this from memory. I think it's a copper carbonate hydrate, maybe. But you're dehydrating the rock, and you are also decarbonating. That's not a word, but you're pulling the carbonate out of the rock as it reacts with the carbon monoxide and the oxygen in the air, in this hot air that you're making, and what you end up with is nothing left but the copper. And the way it looks visually, it's hard to describe this in words, but you start with this green rock and you heat it and it gets glowing hot, and students are like, okay, is anything happening? You're just making the rock glow because it's hot. But then after a couple minutes, you take away the flame and you let it cool down, and it's still red. And they're like, why is it red? Well, you tell me. You took high school chemistry. What does a color change indicate? And they're like, oh, chemical reaction. So we go through this, and then I pull out these little red rocks that I've made, hit them with a hammer, and they don't break. They're ductile. They smush. They smear. And so then it's just another one of those, I thought ceramics were brittle. What happened? And eventually someone is like, oh, it's red because it's copper. You turned it into a metal. Yeah. So wonderful demo. Love that. I learned that from Kevin Jones, actually. Props to him for being my inspiration on that one. But yeah, I love that for sure.
I even like, if you watch carefully, once it turns to copper, the flame from the blowtorch, you start seeing little bits of green.
Green.
Because you might remember from your inorganic chemistry lab course that the color of the gases tell you something about what materials are there. So it's kind of cool. Anyway, there are tons more demos. I think we're out of time. I just realized this. We're at the 45-minute mark.
Oh, my goodness.
So
talk about demos all day, but I won't. We should wrap it up.
So we'll wrap this up, and let me play our outro music. So with that, thanks for joining us, and we'll see you next time.
See you next time.